Hi everyone. This is the last video where we deal with homogeneous systems of differential equations, and it's going to be when we have some repeated eigenvalues. I've got three examples here that I wanted to show you. The first one is unique. The second one, I'm going to introduce some vocabulary and a new system for solving these when you have repeated eigenvalues. And then the third one will just be a quick example just so you can have another reference point and see what it looks like in real time trying to solve it. This first one here, and I'll start with, I decided to show it to you in this form where I already have it in matrix and vector form. Because I want you to think about converting this back into system form, right? So this one, if I want to convert this into system form, I have two equations, y1 prime and y2 prime, and that's going to be equal to, respectively, this is going to be 2 times y1 plus 0 times y2, and this one is going to be 0 times y1 plus 2 times y2. Now, this one's a little bit different from what we've been looking at before with our systems of differential equations, because this y1 prime only depends on y1, and this y2 prime only depends on y2. So way back in chapter 2, or even the first day of class, if I gave you a differential equation that looked like this, y prime is equal to 2y, you should be able to solve for y. You should be able to find the solution for this. So for this one, it turns out that y1 is going to be equal to e to the 2t. Right? If y is equal to e to the 2t, or maybe a constant times that, then 2 times that should be equal to y1 prime. Same thing here. We get that y2 is equal to e to the 2t. When we solve the system in this way, we are really looking for solutions that are coming in this vector form. Right? So right now we have solutions for y1 and y2, but if we want to solve it in the way that we've been having solutions for this, or if we want to solve them in the same form that we've been solving them in, we need to do a little bit more work, but we'll see this e to the 2t and e to the 2t reappear. So I'm going to continue kind of in a normal fashion where I try to find my eigenvalues by looking at the determinant of my A matrix minus lambda I. And setting that equal to 0. This means that the determinant of 2 minus lambda, 0, 0, 2 minus lambda, the determinant of that is equal to 0. So my characteristic polynomial minus 0, right, is equal to 0. So I get that my eigenvalue, lambda 1 and 2, is equal to 2, and that is repeated. And I'll be using this vocabulary later on in this chapter and in the second example, but we would say that this eigenvalue has a multiplicity of 2 because we have 2 instances of this here. Anyway, it's repeated. And if I just sort of ignore the fact, if I try to find my first eigenvector here, if I just try to find my first eigenvector here, then the equation that I'm going to use is that A minus lambda I times my eigenvector should be equal to the 0 vector. So I get this matrix 2 minus 2, 2 minus 2, and we end up with a situation that we haven't seen before. So this is our augmented matrix, and in this situation, we've seen this before. This gives us a degree of freedom. And this line also gives us a degree of freedom. So we get to choose any values for our eigenvector. The one thing that we need to think about, or rather two things, we need to make sure that our eigenvector is not equal to the 0 vector, right? We can't just have zeros, so we couldn't use x1 equals 0, x2 equals 0. And we also want to make sure that x1 is linearly independent better phrasing here, that the eigenvectors x1 and x2 are linearly independent. Okay. So those are the two things that we want to think about when we're choosing our vectors here. So I'll maybe put this in a different color. But as long as we keep those two things in mind, then we can pick whatever we want. We have that degree of freedom. I'm going to choose x1 equal to 1, x2 equal to 0, and that means that my first eigenvector is equal to 1, 0. For my second eigenvector, I want something that's linearly independent, or I want a vector is independent from my first eigenvector. So I choose sort of the quintessential set of independent vectors, which is just going to be 0, 1. So this is my first eigenvector, 1, 0. My second eigenvector is going to be 0, 1. This one is a really special case. The first example that I just showed, we'll have a more kind of rigorous way to pick some linearly independent solutions that we get here that won't be the zero vector. But for this example, if you end up with a situation where you have repeated eigenvectors and you have 2 degrees of freedom, that means that you're just allowed to pick 2 linearly independent eigenvectors. So my solutions here I get that my y1 is equal to e to the 2t times 1, 0. Y2, my second solution, is going to be equal to e to the 2t times 0, 1. What this means is that my general solution is going to be y vector is equal to c1 e to the 2t, just written out like this, plus c2 e to the 2t times 0, 1. Now, if I want to write my solution matrix, if I want to write my solution matrix, that's going to equal, I'll say in terms of t. So I just use the columns y1 and y2 on here, so I get e to the 2t, 0, 0, e to the 2t. Now, I mentioned a solution that works up above here, where we can say that our solution for y1 is equal to e to the 2t, and our solution for y2 is equal to e to the 2t.